This video is the second video to accompany the Merg Beginner's Kit 101. In this video, we will connect up and test the modules that were built during the first video. A further video will cover configuration and use of the modules. The first requirement is a set of modules that have been built, along with the various components from Kit 101 that have not been used yet. Another careful visual examination of all the solder joints at this stage can save some heartache later on. You will need some hookup wire. 5 different colours will be useful. For the short lengths used here, the size is not too important. If the modules are used on a layout with longer wire runs, larger wire may be required. This is especially true for the power supplies, to avoid excessive voltage drops. Technical Bulletin LC01/01 gives useful information about different types of wire and helpful advice on how to wire up a layout. Some nylon spacers are supplied with Kit 101, and you will need to source some screws or nuts and bolts that fit through these spacers. You will also need various screwdrivers, some wire cutters, and a means of stripping wire. A wide variety of types of wire stripper are available, some more successful than others. Some types work better on a particular size of wire. Personally, I just use a scalpel to cut the insulation neatly by rolling it to and fro, then pulling off the end. You will need to use the power supply that comes with Kit 101. If you're in the UK, a figure of 8 power lead is supplied with the kit. If you're elsewhere in the world, you need to source locally a figure of 8 power lead with a plug that fits your mains outlet. You also need to use a multimeter. These come in various shapes and sizes, but basically any one of them can be used to measure voltage, current, and resistance. This type has a slider switch to select voltage, current, or resistance measuring mode, and a rotating knob to select the measurement range. We will be measuring 5 volts and 12 volts, so a 2 volt range would not be of use, and neither would a 2000 volt range. A 20 volt range should suffice. This type is auto ranging, so the rotating knob just selects voltage, current, or resistance measuring mode. It is useful to mount modules on a suitable offcut of wood when testing and initially setting up. It's easier to handle and see what is happening with everything together on your workbench, rather than distributed around the layout, often hiding underneath the baseboards. A piece of wood just under 23 cm by 15 cm is ample for these modules, and will fit nicely inside the box the kit was supplied in. This is useful for storage and for transporting to area groups, when that is allowed again after social distancing. Determining the best position for each module, making sure nothing will be left hanging over the edge of the board. My piece of wood is thicker than absolutely necessary. A piece of MDF would be better if I could have found one. The nylon standoffs have a habit of wandering off on their own when unattended, especially when trying to fit modules underneath the layout. So now I superglue them to the 4 corners of each module, taking care to fit them centrally around the screw holes. This saves a lot of searching later on. Screw or bolt the 2 modules to the board. 2 screws in opposite corners will suffice, as this is only a temporary for testing and setting up. The experimenter's kit modules sit lower than the main modules and can lie directly on the wood. I put 1 screw in each to hold them in place. The power connector was intended to just dangle free on the end of 2 wires, but I made a simple clamp from a piece of wood and 2 screws to fix it in place, while still allowing access to the terminal screws. Using different coloured wire for different purposes really helps to avoid errors and assists in fault finding. The actual colours used does not really matter, so long as you stick to your colour code throughout. A label helps to make things clear. You could just write on the wood with a permanent marker pen. 2 wires are required to connect the power connector to the input terminal block of the CANAC 8. I use black for the 0 volts and red for plus 12 volts. Strip the ends of the 2 wires. The power connector terminals are marked with a plus and a minus, but these markings are hidden by my clamp. On the CANAC 8, the terminal nearest the diode is the positive, and the one by the wire link is negative. Fit one end of a wire in the terminal block, making sure no strands escape or stick out. Tighten the screw firmly, and then give the wire a tug to make sure it is secure. Fit the other end of the wire in the power connector terminal. Tighten the screw and again check it is secure with a gentle tug. Repeat the process for the second wire. Accidentally swapping these connections will not damage anything because the diode will protect the module. However, nothing will work until the wiring is corrected. Now you can plug the power supply into the main socket and plug the power lead into the power connector on the test board. After a few seconds, check that the 2 voltage regulators are still cold. If either is getting warm, disconnect the power. There is a short somewhere, so you will need to check all the solder joints for any stray whiskers of solder making unwanted connections. If everything remains cool, keep the power connected and we will start checking some voltages around the module. First, check the voltage of the power supply entering the module. This can be measured between the wire link and the ends of the diode. This should be about 12 volts at the end of the diode closest to the terminal block. The voltage at the other end of the diode will be 0.7 volts lower. Integrated circuits usually have a small indentation or cutout at one end, indicating where pin number 1 is located. Sometimes it is marked with a dot, or more recently by a chamfer down the side. From pin 1 in the top corner, the pins down that side are numbered 2, 3, 4, etc. to, in this case, 9. We then pass across the bottom end to find the next pin, in this case number 10. We then count up the right hand side for subsequent pin numbers 11, 12, 13, up to, in this case, 18. It is important to remember this pattern, as we will need to find the specific pin numbers on the 8-pin and 28-pin integrated circuits to check some voltages. First, we need to put our negative probe into the socket for pin 8 of the PIC, labelled U3. The positive probe goes into the socket for pin 20, so we count down to pin 14 and then back up the other side from 15 to 20. The voltage here should be about 5 volts. The 8-pin socket is the other way round to the other two. The negative probe goes into the socket for pin 2 and the positive probe into the socket for pin 3. Again, this should measure about 5 volts. Now take a short length of wire and hold one end in the socket for pin 8 of the PIC. Touch the other end of the wire on pins 8 down to pin 11 of the socket for U4. Each of the LEDs on the experimenter's board should light up. Warning, do not touch pin 10 at the end, as this should be at 5 volts and our wire would short this down to 0 volts. Now move the wire from pin 8 to pin 20 of the PIC socket. Touch the other end to pin 27 and the yellow LED will light up. Touching pin 28 will light the green LED. Now unplug the power connector. If all our tests were successful, we are now ready to add the integrated circuits to our module. Static electricity can damage electronic components. Some devices are more susceptible than others. In fact, the CAN bus driver seems to be more prone to damage than many other components. Sometimes the damage will immediately stop the component from working. Sometimes it will just shorten its working life. There are measures you can take to limit the threat of static electricity. You can get anti-static wristbands. Unfortunately, I have mislaid mine at the moment. You can ground both hands on a radiator or a water pipe. You can work on a tin lid or a sheet of tin foil. The important thing is to keep both hands and the items you are working on in touch, so that no static potential difference can build up. The black plastic foam is conductive anti-static material, so touch both hands on the material before touching the components that are pressed into it. We'll start with the output driver IC. Remove it from the foam. Notice the legs are splayed out. It will be difficult to fit it into its socket like this. Gently bend the legs inward on a block of wood until they are about parallel. Check the cutout or dimple that marks the top end of the IC is the same end as the corresponding cutout in the socket, and start getting all the legs into their sockets. Check they are all in the right place, and then firmly press down into the socket. Check that all the legs are where they should be, and have not bent sideways, inside or out, and check that the IC is seated right down in the socket. I have a handy gadget for making the legs parallel. This is especially useful with larger ICs like the 28-pin PIC. Pop it in, squeeze, and it's done. Double check it is the right way round. This one has a cutout and a dimple indicating pin 1. Line up all the legs and then press firmly down all along the length of the IC. Check all the legs are correctly in their sockets and none have bent the wrong way. The CAN driver IC is last. Note that it is the other way round to the other two ICs. Press into place and check. Now we can plug in the power supply again. The green LED should light up. It actually indicates that the firmware in the PIC is running. After a couple of seconds, check the voltage regulators are still not getting warm. If one is, unplug and check everything again. Now we can check some voltages again. The voltage between the diode and the wire link should still be around 12 volts. The voltage between pins 2 and 3 of the CAN driver IC should still be at 5 volts. Take great care not to bridge the gaps between the legs with the meter probes. That is all the testing we can do now, so unplug the power and we can connect up the other module. We need 4 wires to connect the modules, 2 for CBUS and 2 for a 5 volt power supply. I had already specified colour coding for the wires, so I've cut 4 equal lengths and stripped the ends. I have also picked a 68 ohm resistor from the experimenter's kit bag. Normally, CBUS would have a 120 ohm resistor at each end to terminate the bus, but for a short length like this, a single 68 ohm resistor will suffice. The 68 ohm resistor is colour coded blue, grey and black. The resistor leads are bent and trimmed so they fit into the terminal block of the CAN 8 labelled H and L. One end of the blue wire is also inserted into the terminal marked L alongside the resistor lead, and the terminal screw is tightened down on both of them. A gentle tug on the wire and resistor confirms they're secure. One end of the yellow wire is inserted into the terminal marked H alongside the resistor lead, and the terminal is screwed down tight. Again, a gentle tug confirms everything is secure. The blue and yellow wires form the CBUS. One is CAN H and one is CAN L, and on larger layouts it's important not to swap them over. The 68 ohm resistor is now terminating our bus. The orange wire is inserted into the terminal labelled plus. This is a 5 volt power output from the CAN 8 and will be used to power the CAN 8C module. Finally, the black wire is inserted into the terminal marked with a 0. Make sure all the wires are secure. Now the other ends of the 4 wires can be fitted to the corresponding terminals on the CAN 8C module. This is easier as there is no resistor to worry about. Again, make sure all the wires are securely held by the terminals. And that concludes the wiring up. Plug in the 12 volt power supply again. The green LED on the CAN 8 should light up, but no other LEDs should light up. After a few seconds, check the CAN 8 voltage regulators again to ensure they are both remaining cool. Now we should check the voltage on the CAN 8C module. Measure the voltage between pins 19 and 20 of the PIC socket. It should be about 5 volts. Now take a short length of wire and stick one end in pin 20 of the PIC socket. The yellow LED should light up when the other end touches pin 27, and the green LED should light up when pin 28 is touched. Unplug the 12 volt power supply again. The CAN 8C integrated circuits are supplied in a plastic tube, which should be anti-static. I emptied the tube out onto the black plastic foam that came with the CAN 8 to keep the ICs safe until I was ready to install them. The leads of the ICs need to be made parallel, as before, to make fitting them easier. Check carefully the pick is the right way round, locate it into the socket, and then press down firmly. The same goes for the CAN driver, which is the opposite way round to the pick. Check all the legs have correctly entered the sockets and have not bent off in another direction. The switch blocks on both modules should now all be set to their off positions. The switches on the experimenter's module should also all be off. Plug in the 12-volt power supply. The green LEDs on both modules should light up, showing that the firmware on both modules is running. Check the voltage on the CAN ACE 8C module. This is easiest using the two ends of the connector to the experimenter's module. It should still be about 5 volts. On the CAN ACE 8 module, switch number 5, which is indicated by an L on the circuit board, should be switched to on. On the experimenter's board, the switch labelled 1 on the circuit board should be switched on. Switch 5, labelled L on the CAN ACE 8, should now be switched off again. The experimenter's module switch 1 can also be switched off again. Now, when the experimenter's module switch 1 is switched on, the LED labelled L8 on the other experimenter's module lights up. Switching off extinguishes the LED. So, 50 quid and a few hours work, and we have a switch that turns an LED on and off. Wow! However, in the next video, I will show you how much more these modules are capable of. More modules, the same or different types, can be added to your CBUS to perform specific functions, or provide general purpose connections, or to bring logic and computation functionality to your layout. What it builds into is limited only by your imagination and the ingenuity of Merg members developing exciting new modules. So, in the next video, I will show you how to configure your modules in slim mode and explain a little of what CBUS is all about.